Alright, just in time for Thanksgiving, something to be thankful for, a really hard problem. Not sure if I actually am. Anyways, let's see. Pass in matrix whose sum is divisible by k. You're given 0 to index m by n. Enter your matrix grid and enter your k. You're currently at position 0, 0, and want to reach position m minus 1, n minus 1. So you're at the top left going to the bottom right. Return the number passed for the sum of the elements of the path is divisible by k. The sum of the elements of the path is divisible by k. Since the answer may be large, return modulo 10 to the 9th plus 7. Okay. So here k is 3, so then the number paths, remember the sum of the elements in the path is divisible by 3. So 5, 5, 2, 4, 5, 2, 7, 11, 16, 17, 18, 5, 3, 0, 5, 2, 8, 5, 15. Okay, so first thing first, I think I can convert each number to its equivalent in the modulo base. So like this base 3, so I convert 5 to 2, 2 to 2, 4 to 1, 5 to 2, so 7 to 1. Basically take the value, convert it to the remainder of it, divide by k, because those are going to be equivalent in getting to 0 and eventually getting it to be remainder 0. So that's probably the first thing I'd do. The value in the grid is 0 to 100 anyway, so I guess it's not that big a deal. How to approach this? I guess at each, so the path is what exactly? Can the path be like completely labyrinth, like completely snake-like? You want to reach moving down or right? Okay, yeah, so it's actually always moving towards the bottom right. I feel like this is actually somewhat doable as a hard problem. So for each position, I think I go to the next position and store the number of ways to get to the next position with each of the k possible remainders. So if I start at 5, that's the remainder of 2. So that means I can go to this position with a remainder of 2 one way, and go to this position with a remainder of 2 one way. Combine that with the value there, and then go to the next position with those values. Add that possibility to the neighboring cells. Question is how you, how do you How do you do this processing in some ordered fashion? So maybe the ordering is you do it based on everything a certain number of steps away from this origin. So you do everything that's one away from the origin. 2, 3, 4, 5. Is that going to be too long? It's going to be too long, I think. 5 times 10 to the 4th. 5 times 10 to the 4 times 5 times 10 to the 4th is 25 times 10 to the 8th, which is 2.5 billion, I think. 10 to the 25 times 10 to the 8th is 2.5 times 10 to the 9th. 10 to the 9th is a billion, so it's 2.5 billion values in the grid. So I can't just iterate over every single position in the grid, which is quite disturbing. Oh no, wait. That's just the size of one dimension, but the total space is 50,000. 10 to the third is 1,000. 10 to the fourth is 10,000. 50,000. So there's, if you iterate over 50,000, and k is what? K is 50. 50,000 times 50 is 250,000. No, 50,000 times 50 is 2.5 million. That's a fairly big amount. So I think you need to, for each position, iterate over all the possible k values. Is there some optimization there? Alright, I think this is enough to start actually giving it getting a solution, even if it might time out. So every position of grid I want to have k size array of the number of paths to get to that position with a certain remainder. Okay, so I think it's going to be, I'll call this paths matrix, and I'll go ahead and create the rows and columns variables from the grid. So it's going to be length of the grid is the number of rows, and length of the first row in the grid is the number of columns. And then paths would be, I guess, starting with 0, 1, maybe everything is 0. Everything starts with zeros, maybe. 0 times k. This is going to be a 3D matrix for every spot. I think it's going to be 3D matrix. Yeah. 0 times k for 0 times k for every row, for every column, and then for every row. I don't know if this is bracketed correctly. I think it should be bracketed like this. Okay, let's go ahead and just see if this is correctly sized. And I'll use a test case here. So let's say my test case is case 2. So it should be 3. Let's go ahead and size it so it's not a square matrix. So it should be a 2 by 3, 2 rows, 3 columns, and each spot has a 2 by 2. Has 2 things. Yeah, 2 by 3, each spot is an array of zeros. That's size 2. Okay, which is the number for k, which is the remainders. And then I think normally you want to initialize something slightly different. And I think the starting pass is 1. The number of ways to get to the first cell is 1. And then I modify everything based on that. I guess maybe I can use a for loop or I think I want to use what's the 0010012011 1 these all up to 2, these all up to 3, the row and column adds up to 3, 4 and 5. How do I iterate over those particular things? Should be a pretty straightforward way. I think I maybe start with maybe I have a set of cells, set of tuples that are the row and columns to iterate over. Okay, so maybe I have current positions is going to be 0, 0, and then I think maybe something simple like while current position exists, I'll have my next positions be a set, and eventually the current position equals the next position. Technically this should probably be a set, so maybe and then maybe something like a simple check. I'll do is valid for a particular row and column, turn true if it's that row and column is number of rows and columns. So I do some stuff and then I need to add something like if I guess it's current position, while current position, I think I need to iterate over everything inside the current position, so it's going to be, this is a set of tuples, this is a set of positions to evaluate. So for every position there, so it's every RC in current position should be defined for that. declared before that. And then I do something where if is valid r plus 1, so same row, different next column. Then next position dot add r c plus 1 position if the also is valid. The next row, the same column. This is going like from a certain position moving to the other side, so that it's kind of doing this kind of backwards. This part is technically after the evaluation of the current cell, but this is straightforward enough that I don't want to forget it. Okay, so it's going to add the positions of the neighboring cells in the kind of diagonal higher distance. And this is set, so it's going to remove any duplicates from there. I think that's fine. Okay. And then, so evaluating a particular position. It's going to go through every possible. So it needs to first get the value here. So let's say the value is the grid at this position mod k to make it the equivalent in the base of the modulo. And then it's going to, actually this actually is part of the thing, huh? So if it's valid, then modify the number of ways to get to that neighboring cell. So let's say the current path is paths for this row and column. Paths for this row and column. I guess here I can say next path is the paths for the same row adjacent column. Next path is that. And then I need to combine these two. So for every remainder in range of k, for every remainder in range of k, the value plus the next path. Okay, say I call this remainder. I call this rem. The remainder path of remainder plus the current value. I guess this should be mod k. Is added with the current path for that remainder. So if the number of ways of getting to this, this should not be 1, 0. This should not be 1. This should be like 1 and a bunch of zeros. Like there's one way to get to the starting spot with a 0 remainder, and 0 ways to get to the first spot with any other remainder. So I think maybe this should be 0, 0, 0. First position, first remainder, or first position with 0 remainder. I guess that makes sense because it's 3D matrix, right? So the current path, so the number of ways to get to the current path with some remainder added with the current value, so the remainder changes by that much, is going to be changed by this number of paths. So I think this is right. I think that's right. I'll find that shortly when that's right off. Alright, so here, same deal. Next path is the paths. Next path being the adjacent path, or the path to the adjacent cell. Paths row plus 1 column for every remainder in range k. Next path of remainder plus value mod k added with that path of remainder. So this is like, let's say I'm here, there's actually two ways to get to here, either the top or from the top and from the side. So it's from here I combine those two. I wonder if there's a better way to do it. So there's only really, this is not like a graph, or a graph might be somewhat trickier. I just know that there's exactly two ways. Oh, what? So that should get me to the last position, where the last position doesn't actually have any valid adjacent thing. So therefore, I think I can return. So the next position would be empty. The while loop would stop. So I think I return the last paths of I think it's going to be row position, column position. Row position is the last row, last column, and getting the remainder of 0. I think that might work. Okay, interesting. Less than. Okay, first thing's wrong. So let's go ahead and print out the pass, I guess. Okay, so first row, so the very first cell, there's one way to get there with remainder 0, it's fine. And then in the next cell, I'm going there with a 2, so there's one way to get there with a 2 remainder. Yeah, this remainder is 2. And then from there, getting to the 4 is going to be a remainder of 1, because 2 plus 2 is 1 base 3. So it's getting there, one way to get there with 1. That's fine. And then the second row, there's one way to get there with the remainder of 2. And here, so I can go here to here, and there's one way to get here with the remainder of 1, and one way to get here with the remainder of 2. Okay. This seems to be working. Third row, or last column in the second row. So from the top, there's a remainder of 1 plus a 1, so there's one way to get here with the remainder of 2. lost track of things here. 1, 1. Yeah, this seems fine. 1, 2 seems fine. 0, 0, 1, that seems fine. Moving to here. 0, 0, 1 plus the 1, 1, 2 plus the 0, 1, 1 is going to be 0, 1, 2. Alright, so 0, 1, 2 plus 5 is remainder 2. So that should be shifted over 1, 2. So it'd be 1, 2 here. It should be shifted over 1. So 1, 2 here. Shift it over 2. Shift it over that. I think shift over that amount. I think it does. 5 shifts over. So 1. So there should be 1 there. 7 shifts over once. So it should be 3. It should be 2. A double counting pass. Double counting pass. I think I am. Where's it? Actually no way to get to the 7. Right here it's saying that there's 2 ways to get to the 7 with remainder 2. But there should actually be no way getting to 7 with remainder 2. I think I know what screwed up on. Yeah, it's need to take into account the last value. So the last value is always 0 in these ones. Yeah. It's getting to the last value and then it's not adding the last value into the remainder calculation. So it's the complement of the last values thing. So it's not 0 here, it's k minus value mod k, something like that. So 2 needs to actually get 1 as the complementary remainder to get the sum of 0. So it's like k minus the value here, mod k. What is the simplification of that? K minus value mod k. I guess I could just do 2 rather than just try to do a complicated expression. I think I can just do something like the complementary value is going to be bid at the last spot mod k, and then just k minus that value. Okay. Grid at -1, -1 mod k. That Well, k minus complementary. I guess, sure. I think if k is k minus 0, if the complementary is 0, then it should be k. I could do k minus complementary mod k. Seems a little bad. Let's I think I could just do k minus this thing mod k. Oh. I'll call this the yeah, it should still be called complementary, I guess. Is this fast enough? Oh boy. Oh. The big thing that they said, which was take the module of everything. Wonder if I need to take it. If it's slow enough that. Yeah. Just play a bunch of mods here. Okay. Decent. Could be faster. I'm glad this wasn't terribly hard compared to some of the others that were straight up never solved. This could be faster though. Could be. There's some solutions that are half. No, it's actually 3 times faster, 3 times faster. What is slowing this thing down? The way that I'm iterating over the positions is a little inefficient, I think. Oh, it's not a little, it's just very inefficient. How to do it faster though? Yeah, there's no need for this sort of. No need for this to be this slow in terms of figuring out where to position. Because this always going to be here, then here, then here, then here. Could do a single. Could do a single. What can I do here? Do a single list of positions, set of things that are added. This should not be the hardest part of this problem. The traversing of the positions so that it's diagonal. Like first, second, third, fourth, fifth, sixth, seventh, eighth. Does it even matter? every distance from 1 to n plus n, and then for every combination of row, starting with the row is equal to 0. So here, so it's row 0, row 0, column 1, row 0, column 2. Okay, so I think I just need to do a nested for but then here's row 0, row 0, column 1, 0, 0, column 2, row 0, column 3. And then let's go through all the rows, and then for every starting column position. And then once it finishes that, then it needs to go through from the last row, and then from the first row, every possible starting column, reversing backwards. So row 0, column 2, column 1, column 0, and then row starting with this is so complicated. Could just make use of a set of things that I've seen. A matrix of stuff with positions that I added. Have a queue. Have a stack. No, have a queue. Have a queue of positions. Yeah, it's the same thing as fucking sets. Traversing it. I'm pretty sure this is slowing down because of traversal. Well, I know this is slowing down because of traversal. It's just whether or not that is the optimization that's gonna get it to where it's really fast or just slightly improved. There should be some sort of simple formula for this. So if I increment the distance as the outer loop, distance is 1, distance is 2, distance is 3. And then I go through every valid combinations of row and column for that distance. So row is equal to 0, column is equal to distance minus the row, if that's a valid if that is valid, row is equal to 0. So starting with row 0, column, distance minus row, iterating from that to the distance. If it's not valid, skip. That's definitely fine. Maybe I Can also ignore the is bunch neighboring cells. That might be workable. Okay, so reformulating this. Standard. Traversal or diagonal pattern using sets. Okay. So let's say for every distance in range of, I guess it's 1 to r rows plus columns, something like that. A rows plus column plus 1. So rows 3, 3, distance 1, 2, 3, 4. Why isn't it more than that? So 3 by 4, distance 1, 2, 3, 4, 5. Rows plus columns minus 2, because you can't actually go minus 1. Okay. 1, 2, 3, 4, 5. Actually, maybe it's just. Actually, maybe it is just rows columns. Okay, I just need to go through these. I don't actually need to process this. 1, 2, 3, 4. 1, 2, 3, 4. So actually it's minus 2, right? 3 plus 4 is 7, minus 2 is 5, so it goes from 1 to 5, which stops before 5. So this is 3 plus 3 is 6, 6 minus 2 is 4, 1, 2, 3. And this is 1 plus 2 is 3, 3 minus 2 is 1. So 1 to 1, so it doesn't actually ever do this, actually. 1 plus 2 is 3, 3 minus 2 is 1, 1 to 1. So it never actually does this one. It's wrong. Maybe I do need to evaluate at 0. No. That's right. I need to actually go from this position to this thing. So. Okay, every distance. So the values of this distance is going to be for every row, say r in range of 0 to distance, so distance plus 1. Let's run this. So distance plus 1. And then column should be the distance minus the row initially. And if this is not valid, then skip it. Because it could possibly go out of bounds here. Actually, it's like a 2 by 3 or something. Or 3 by 2. Could be in row 3, column, whatever. Actually, I wonder if I can remove the check for whether or not the neighboring cell is valid just by making the size of the size of the grid of the paths matrix one dimension larger. Even if I never iterate over those particular positions, I can have those positions be kind of dummy. So that would just mean it would be columns plus 1, rows plus 1. So then I have to check if R C plus 1 is valid, because then C plus 1 is always valid, and R plus 1 is valid because it's extra row. So I think this should be value equals grid at row column mod k, and then current paths of current path is paths at this row and column, and then for every remainder in range of k, next I guess I can do right adjacent. Right path is going to be paths at R C plus 1. Bottom path is going to be left, right, top, bottom, left, right, left. Bottom path is going to be paths at row plus 1 column. For every remainder, next path of, I guess this can be bottom path, remainder plus value, mod k plus equals the current paths, I guess current path. Every remainder mod k, or mod, and then that's the right path, and same thing with bottom path. Path of remainder okay. This is, I don't need this set anymore, and I still need that same ending. Find the complementary of the last value, and then return that. Oh boy. Wait, never stored, no, I did store this back in the grid. I'm guessing this thing didn't change the passive, that's for some reason. Oh, it's because I modified the sizing of it with a dummy row and dummy column, so it should be -2, -2. Okay. So let's see how this, I think, improved traversal of the positions in the grid bears. Oh boy. Goes infinite. Or just go too slow. Interesting. What is the dimensions of this? Okay, yeah, I see. the other one did have an improvement in the sense that it didn't actually attempt a lot of out of bounds positions. Here it's the 5,000 by 1, so it's actually going to pretend that it's a 5,000 by 5,000 or 50,000 by 50,000 and traverse every single combination of those rows columns. Okay, I just need to modify this, I think, just to make it start at a better spot. So for row in range R, so it starts at row 0 always, and then starts in row 0. Distance is so it starts in row 0 for every distance, which is probably fine. Starts in row 0 for every distance. Row 0, column 0, row 0, column 1, row 0, column 2, row 0, column 3, row 0, column 4, column 4 is not possible. I think it should probably start in this one, it should be row so let's just start row 1, that spot then. So the minimum row should not always be 0. Because if it's a distance 5, it should start row 1. So it should be the minimum of, or the maximum of 0 and distance minus column. The distance is 5, and then column is not actually, oh, distance minus the total number of columns. I think that's the maximum of that. Yeah, that's, so it's going to be the maximum of 0 and distance minus number of columns. I'll make this into an actual variable. Min row is going to be max of 0 and distance minus columns. And this starts with min row. Just to decompose that a little bit. So if the distance is 0 and the number of columns is 4, then it actually starts with 0. Distance is 1, distance is 2, distance is 3, distance is 3, distance is 4, 4 minus 4 is 0, that should be 1, so distance minus columns plus 1. Because I want the min row to be 1 at that point. I think that's right. Oh, unfortunate. Oh, I think I still have the test code, test blocker. Still too slow. would that be the case? Oh, yeah. I need to immediately break when it's impossible, I think. So if it's not valid rather than continue, I think this actually should be not valid. I was thinking with this, like, there should be two kind of stopgaps. One is the row is too bad, and the other stopgap is the column's bad. Yeah. Well, that was a lot of work for no gain. No gain. Worst game. Oh my lord. Well, that's pretty bad, huh? Is this how I'm gonna end it? I mean, in theory, this should be faster traversing, right? This literally goes to the next thing without having to do sets to figure out where the next thing is. I mean, I guess maybe I could not have this extra bit here. Hmm. I wonder. I did it the reverse way rather than thinking about iterating over the starting directions but the ending cells, where the ending cells added the paths from the top direction and the left direction. I mean, that might cut down the operations rather than having two different. I'm not sure if that really makes a difference. Rather than doing two different assignments, you're doing two different, adding things from the previous paths. And there'd just be one single conversion. Is that any better? I guess with one single conversion, you maybe. Alright, I'm gonna try this one last thing. So this is iterating over the starting cells and then kind of pushing the paths to the destination cells. But now I'm just going from the destination cells. So here, I think I still want the initial thing. Do I? Distance is going to be starting with 1 maybe. Distance in range of 1. that right? I'm gonna go with what my gut tells me. I think this should be starting with distance of 1. And I think that means I do need rows plus columns minus 1 rather than 2, so I actually end up being this spot. Then row is going to be row 0 still. This is still fine. If it's not valid, then break, that's still fine. Is it? Grid. So this is current path. I'll go backwards instead of top path, or left path and top path. The adjacent ones from those directions, those be paths. Same row column minus 1, row minus 1, same column. The other remainder from the current. Oh boy, this is going to be a little tricky. Current path for this. What's going to be here? Current path for some remainder is equal to the left path. I think it probably should be remainder minus value mod k. Yeah, remainder minus value. Guess it could probably be an assignment for the first one and an addition for the second one. Or just a straight up assignment. Left path and then top path. Remainder minus value mod k. And then make that all modular. The other thing I could possibly try to do is, I'm not sure when I should be doing mod. And then this means the last thing is in fact included. Is that right? So maybe this is just going to be 0 here. Not sure. Might be a little too much changes. Oh boy. Well, that actually ran. No, that's just test cases. It was maybe running faster. But I think this is the same issue as before when it didn't do the last thing correctly. I thought I did the last thing correctly now. Current path, this value for this remainder. Is it getting to the last distance? So there's a dummy row, which is, I think, that's the dummy row right there. That's the dummy column in the actual last row. So this should be 3, 2, 1. Don't know if it's actually doing the last one. Guess I can just print out the thing that's doing. The last one I did was row 2, column 2, 0, 1, 2. So it should be doing the last one, right? 2, 2. Huh. Every remainder in K, current path to this remainder. Current path to this thing. For that remainder. Let's just set that. I think so. The number past the first cell. Remainder 0 is 1. This looks like the original thing that I had. 3. So it should have been 2. So it looks like I might still need to do the complementary stuff, but I'm not sure why I need to do it now. So I'm pretty sure the answer should be something like this. It should just be complementary here. Pretty sure that's the correct answer, but I don't know. I guess it didn't work. Okay. So 2 by 3 only goes to 1 by 2. Oh, that's actually the last cell, that's right. Index row index 1, column index 2. Distance in range 1. So you go from either the top path or the left path. Remainder minus the value. Left path, row, column minus 1, top path minus 1, column. Current path. Mod K. Combine. What is special about this? Okay, test case. Let's do something simple here. Let's say it's 2, 3. That didn't work for some reason. Seems like a very big matrix. Okay, yeah, it's k is equal to 5. So 1 is there. Yeah. Yeah, okay. I think I need to actually do distance is 0. Because I need to evaluate the value of this first spot. Eeks. Oh. I'm a dum-dum. Okay. Distance. Actually, this should be fine to do this, but the first thing is not that. It's actually the initial value, which is grid at 0, 0 mod k. The number of ways to get to that first thing with that remainder is 1. Yeah, I think this. Fuck. Grid at 0, 0 mod k. Solve this thing. What? No, I didn't solve this thing at all. So the first spot is 2, so the number of paths to get to the first thing should be 2. Oh, okay, yeah. Now this thing goes back to being 0. Wow, that's a lot of errors compounded. Or maybe trying to fix things incorrectly and thinking about fix something at all. Okay, I think I removed all the rights. Yeah. Oh, wow. Okay, so that was maybe a very, well, still twice as slow as the next most optimal solution, but okay, I'm fine with this. I think that was a pretty big optimization. Well, it was an optimization. I don't know if it was really big. I wonder how costly these mod operations are. I think they should be here. The other operations would be like these mods right here. That should be pretty damn fast. This is all pretty okay. Yeah, this all seems pretty okay. I guess I don't need a function for just this, maybe. But it's always okay to have that starter function, helper function. Monroe. Sure. Guess I don't need to have dummy. No, I do need to have the dummy columns just to. Do I? Yeah, the dummy column is necessary for the row column -1, row -1 kind of indexing rows equal to 0. So that takes something that's actually valid on the other side of the loop of indexing. Okay, I think this is fine. Alright, so summary for this. So keep track of the number of paths, number of ways to get to each position with each possible k remainder, with each possible remainder. which is between in the range of 0 to k minus 1. Using a 3D matrix, which is rows by columns by k. The the eventual answer will be the number of ways to get to the last position, the bottom right, with the remainder of 0. Note that the numbers can be converted to their modulo k equivalent. So for example, if k equals 3, then 5 and 7, 5 and 8 are equivalent to 2, because that's all the same remainder. Iterate over the positions at a certain distance within the matrix, and for and at that position, for each possible value of k, and for each possible value of the remainder, find the contribution of number of ways to get that from the adjacent top and left positions. And that was this thing here. Current path to this thing with the certain remainder is contributed from the left path, taking the value deducted by the remainder. So if the remainder, the current value is 1, and you want to find the number of ways to get there with the remainder of 0, then you do 0 minus 1 mod k, so it'd be probably k minus 1. The number of ways to get to the left path with that remainder, plus, similarly, the number of ways to get to the top path with that remainder. Time complexity is going to be O of rows, well, m and k, where grid is of size n by n, and yeah, since you iterate over each position and for each position iterate over values of k. And then space complexity is going to be O of mn k. Could this have been faster? I guess it could have actually. If we could somehow store an array that is m plus n by k, because at each iteration you can, so m and k using a matrix of all possible positions and kind of ways to get to that position. In theory, could be optimized. So it'd be O of m plus n times k. If using a single array rather than grid for the latest kind of positions that are being evaluated. Because in theory, you don't really use the positions of the previous stuff after we kind of cross-check it. There's like a latest diagonal positions and the next diagonal positions that maybe can be reused in space. But whatever.